Okay, so we are on page 444. Ooh, that's special. In the middle, there's an area of triangle equation. Okay, so area of triangle. The area of triangle is 1/2 b times c sine A, 1/2 AC times sine B, and so on and so forth. So the area of a triangle is going to be 1/2 AB sine C, 1/2 BC sine A, 1/2 CA sine B. Okay, all right. And this is an obscure piece of information that does not come out that often. You probably see it here and then you will never see it again. But anyway, so there you go, that's that. Example number 3. Find the area of a regular octagon with 8 sides, 8 equal angles inscribed inside a circle of a radius of 9. Example number 3, radius of 9, and you're going to have octagon like this. So each triangle you have here, if I blow it up, is going to look like this. And this angle here is what? How do I get the angle measure of here? How many triangles are there? 8 of them, right? So I divide 360 by 8, right? To get 45 degrees. So this is 45 degrees. And I know this is the radius, and this is the radius. They're both 9. So the area of this is going to be 1/2 9 times 9 times 9 times sine of 45. Sine, so this is going to be 81 over 2 times, right? I wrote this especially for Brooklyn because Brooklyn likes it this way.
Yes, this is normal.
Okay, and how many of these do I have in the octagon? How many of these triangles do I have? 8. So the total area of the octagon is going to be whatever I had here times 8, which is going to be 162 root 2. Okay. Okay, that little arc shape there, the shelving at the end.
Yeah.
We're not worried about that. All they wanted to know was the octagon, the area of the octagon. Right. Heron's formula says, given a triangle that has sides of A, B, and C, you can also, in that case, find the area using what a concept called the semi-perimeter. The semi-perimeter is nothing more than the perimeter divided by 2. So the semi-perimeter, this is S. And Heron's equation says that the area of the triangle is going to be this guy. It's B. Okay, so that's what Heron's formula says. I'm not going to go through the proof. I don't need to go through the proof.
Do we have to prove it?
And then example, no, you do not have to know that. Example number 4. So it's basically just a plug and chug. A is going to be equal to A, B, and C is equal to what? 13, 15, and 18. 13, 15, and 18. So if you add all these up, you get 36 divided by 2 is 18. What?
I think your math is wrong.
23. It's 23. So the semi-perimeter is 23. So the area is going to be equal to the square root of 23 times 23 minus this, which is 10. 23 minus this, which is 8. 23 minus this, which is 5.
Moving it along.
Yeah, that's it. That's the answer. And if you do that, you get 20 root 23. Again, there's nothing to it really, right? Measuring a baseball diamond, the bases on the baseball diamond is 90 feet apart. Front edge of the pitcher's round rubber to 60.5 feet from the back corner of the home plate. Find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. Okay, so why would you possibly need to know that?
Figure out how far to run.
And faster.
If I can time how long it takes for the catcher to throw to first base, I can find the velocity if I know the distance.
Yeah, why don't
Just
you
so
that?
fast.
So why does that matter though?
You just
Not
go
gonna
after
actually
that.
I want to hit the ball.
Okay,
When the
so
catcher's throwing it,
Yes.
just thinks of this. Yeah, does he solve it mid run?
90 feet, 60.5 feet. Okay. And am I given an angle? The angle is 45 degrees here. Can I use the Pythagorean theorem here?
Yes.
Why?
It's in the right triangle.
Because this is 90 degrees here? Says who?
It says the book, says the book.
Where?
Right?
Oh, if one's
Wasn't it
45,
45, 90?
yeah.
Does it? I don't think so.
Okay, then how is that possible?
Because it's a square. It's a square.
If the throw, we're taking,
Well,
it-
then where does it say it's a square?
well, when you draw it out,
It's
it's
common
a diamond.
sense.
The diamond.
It's a common sense. Wow, really? So this would be 60.5 too? So this, if you say this is 90 degrees, this and this have to be the same. So this is a 60.5. I don't think that's the answer.
Look at it in the
Sure,
book, it
just
looks
do
like,
it. We'll see what happens.
oh, it's gonna be a tiny bit more.
I don't think
It's
so.
like 91.
I don't think so. So I need to find, I'm trying to find this guy. Okay. This is dumb. A
What's it based
squared is equal to 60.5 squared plus 90 squared minus 2 times 90 times 60.5 cosine 45 degrees. So A is going to be square root of that. And if you do that, obviously you get 63.72, which is not
Equal to
It's
60.5.
which is not equal to
Why don't they just
60.5.
make it 50.5? It's so fun. Like, why don't they just make it-
Actually, I don't know if you guys are, I don't know if you guys are Italians and know this, but they are experimenting by putting the rubber to 61.5.
Ooh, that's stupid.
Yeah. Why would they do that? Like, when it-
They
Yeah,
are
just make it easier
thinking
for
that the
them to-
pitchers are too dominant. They're throwing it too fast.
Last year, that was like the most home runs ever.
So if you push it back, they're hoping that the velocity when it comes to the strike zone is a little less.
Well, yeah, but that's all.
No. So yeah, so you're by moving at a feet back, they're saying that the 95-mile-an-hour fastball would come over the plate as 93 versus 95,
Oh.
which gives the hitter more time to react and locate and hit the ball.
By 1
How are they
foot.
too dominant? Brown?
Huh?
How are they too dominant?
I guess
So
the
there were a lot of home
ERAs
runs.
went really down. Oh yeah, but if you look at the people who hit the home runs, like who?
Trout, sure.
Trout, okay, not Trout, but who was it in the Yankees? Who were the big sluggers?
Judge.
John Carlo and Aaron Judge, right? Aaron Judge has a super high strikeout rate.
So.
He strikes out, well, so basically he's all or nothing. So. All right, anyway, okay, moving on. Let's go to example number 6. Example number 6.
We never have enough. Simon's getting so.
Measuring a dihedral angle. A dihedral angle. So if you have a tetrahedron, which has 4 faces,
I'm not doing 3D
and
now.
each one of them is a length of 2. Okay, can you see where, I'm not gonna even try to draw this. You see where it says AB on that figure 5.28? AB, it has a square root of 3. Can you see why it's square root of 3?
90 degrees.
Because it's,
Because each side is what triangle?
A new one.
triangle.
Equilateral.
Equal, yeah.
Equilateral triangle, right? Because each side is 2. Every single one of them are 2. Okay? So on the bottom, you have ADE. This would be ADE, and each one of these lengths are 2. And I want to know this length. So this is half of this. So this would be 1, 2, root 3, right? That's the 30, 60, 90 triangle, right? So you can see how this guy from here is root 3. So that's root 3. So each one of them would be root 3, and you are trying to find the angle between those. So you have, on that triangle, you have 2 root 3, and you're trying to find this angle right here. Is what you're trying to do. So this angle here is going to be 2 squared is equal to this squared plus this squared minus 2 root 3 cosine, whatever this angle here is. Everybody see that? Did I go too
Probably
fast?
70.
Did I go too fast? This is
Probably about 70.53.
Oh,
Give or take.
4, 6 minus 2 times 3 cosine 3. So you move it over, -2, -6 cosine 3. So cosine theta. So cosine theta is going to be equal to 1/3. So it's be the arc cosine of 1/3, and if you do that, you're going to get 70.53. And we will call it good there. We are done with chapter 5.
Today's Thursday, right?
All day.